Add up every star you can see. Add the planets, the glowing clouds, the gas inside every galaxy your telescopes can reach. It comes to less than half of the ordinary matter the universe is supposed to hold. Not dark matter, not dark energy, the plain stuff, the protons and atoms in your hands and your blood. For more than 20 years, the count came up short, and no one could say where the rest had gone. This was not a rounding error. It was half of everything made of atoms, missing from the map. Then a flash reached us from the far side of the universe, a burst of radio waves gone in 1,000th of a second, after a journey of billions of years. It carried something inside it, and when researchers read what it carried, they found the missing half, resting in a place no one had thought to look. There's a number that physicists can work out two completely different ways. One way looks back at the young universe, at the faint heat left over from the very beginning. That heat carries a fingerprint. From it, you can calculate how much ordinary matter the universe made. Protons, atoms, the stuff of planets and people. The number comes out clean and firm. Then you can count the other way. You point your telescopes outward and add up what you see. Every star in every galaxy, every cloud of gas, every faint smear of light across the sky. You tally it all as carefully as the instruments allow. The two numbers should match. They don't. When you count what you can see, you find less than half of what the first method says is there. Not a little less. Half. As if you weighed a person on a scale, then counted them limb by limb, and the limbs came to half their weight. The rest of the body simply gone, and yet the scale insists it's there. This is real, and it sat unsolved for more than 20 years. Scientists gave it a plain name: the missing baryon problem. A baryon is just the family of particles that ordinary matter is built from. Protons and neutrons, the cores of every atom in your body. So the missing baryons aren't exotic. They aren't strange new physics. They are the most familiar material in existence, the same matter as your skin and your bones, and half of it had no home on any map. Think about what that means. We're good at this. We have telescopes parked above the atmosphere. We can read the light of galaxies so far away that the light set out before the Earth existed. We can measure the leftover glow of the first moments after everything began. And with all of that, we could not find half of the plain, ordinary stuff the universe is made of. It wasn't lost in some far corner. The math said it had to be everywhere, woven through the space around us. Close, in a sense, just invisible. You could look straight at where it should be and see nothing at all. For a while, people hoped the answer was boring. Maybe the count was sloppy. Maybe the telescopes missed some galaxies. Maybe the early universe math had a flaw. Every few years, someone checked. Every time, the gap held. The leftover heat from the beginning kept giving the same firm number. The telescopes kept finding only half. So the matter was out there. It had to be. The universe had built it. And the universe does not misplace half of itself by accident. The atoms were somewhere, in a form we couldn't catch, in a place we couldn't see. That's the strange part. Not that something rare was hiding. Something common was hiding. The most ordinary matter there is, outweighing every star in the sky, and it slipped through every net we owned. Here is the whole universe, broken into what it's made of. Most of it is something no one can see or touch. Around 68 parts in 100 is dark energy. We don't know what it is. We only know it pushes, stretching space wider every second, driving galaxies apart. Then another 27 parts or so is dark matter, also unseen. It has weight and it pulls, holding galaxies together, but it sends out no light and touches nothing we can grab. Add those two, and you've covered about 95% of everything. All of it dark. All of it beyond our senses. What's left is the part we can actually see and stand on. Stars, planets, gas, dust, you. Everything you've ever touched or photographed or held. Roughly 5% of the universe. That's our whole world. The entire visible cosmos, squeezed into a thin slice at the edge of the books. Now go inside that slice, because it gets stranger. Of that 5%, only a small piece is locked up in things that shine. The stars, the planets, the cold clouds inside galaxies. Add all of it, every glowing thing in every galaxy, and you get less than 1/10 of the ordinary matter. Less than 1/10. The bright universe, the one in every photograph you've ever seen, is the small part. So where's the other 9/10 of the ordinary matter? Some of it, scientists could account for. Hot gas around galaxies, thin material they could measure in pieces. But when they finished adding up everything they could confirm, they still came up short by about half. Half of the ordinary matter gone from the count. Stack the problem up, and it gets dizzying. The universe is mostly dark energy and dark matter, two things we can't explain. Only a sliver is ordinary matter. Most of that sliver doesn't shine, and half of the part that doesn't shine couldn't be found at all. So when people say half the universe's ordinary matter was missing, hold on to the scale. This isn't half of some grand total, it's half of the small familiar fraction that makes everything you know. Half of the only kind of matter you will ever touch was unaccounted for. And it's worth being clear about what missing meant. The scientists weren't confused about whether it existed. The early universe math was solid. The matter was made. The question was never if. The question was where. Where do you hide that much ordinary material so completely that the best instruments ever built come up empty? The honest answer for years was that no one knew. There were good guesses. There was a leading idea. But a guess is not a measurement. And in physics, the gap between the two is everything. You can believe gas is spread between the galaxies. Believing isn't finding. You have to weigh it. You have to point at the dark and come back with a number. For a long time, no tool could do that. The matter was too thin to glow, too cool to flare, too spread out to catch. It filled the space we live in, and gave back almost nothing. The universe had hidden the most common thing it owns in plain sight, across the widest stretches there are. And the search for it would lead into the longest, emptiest places in existence, the dark gulfs between the galaxies, where almost nothing is, and almost everything went. The first real clues came from light that had nothing to do with the gas itself. Scientists went looking with the tools they had. One trick used quasars. A quasar is a galaxy with a feeding black hole at its heart. So bright it outshines everything around it, blazing from billions of light years away. Think of it as a distant lamp, far across the universe, pointed roughly our way. Here's the idea. If thin gas floats in the space between that lamp and us, the gas leaves a mark on the light. As the lamp's glow passes through, certain colors get absorbed, the gas drinks them. So when the light finally reaches a telescope, there are gaps in it. Thin, dark lines where specific colors should be. Read the gaps, and you can tell something about what the light passed through. It worked in a way. The gaps were there. They showed gas in the dark, strung along the line of sight. For the first time, scientists had a hint that the space between galaxies wasn't empty. Something was out there, drinking starlight. But a hint is a frustrating thing. The quasar method could tell you gas existed along one thin pencil line through the universe, the exact line between that lamp and your telescope. It couldn't tell you how much gas filled the broad space all around. It was like proving rain exists by catching a single drop. You know it's wet out there, you can't measure the storm. Then there were the X-rays. Some of the missing gas, the theory went, should be hot. Not warm, hot. Heated by the violence of the universe to millions of degrees. Gas that hot gives off X-rays, a kind of light far past what your eyes can see. So scientists pointed X-ray telescopes at the dark and waited for the glow. They caught some. Around the biggest clusters of galaxies where gas piles up thick and blazing, the X-rays came through clearly. That gas was real and it was hot, and they could weigh it. But the clusters are the crowded downtown of the universe. Most of the dark isn't like that. Most of it is the open country between, where the gas thins out and cools and stops glowing brightly enough to catch. Out there, the X-ray signal faded into the background. The instruments strained and came back unsure. So this was the state of the search for a long stretch of years. Real hints. Real gas found in pieces, in the easy places. A growing belief that the rest was spread through the in-between, thin and warm and quiet, and no way to prove it. No way to point at the wide dark and come home with a firm number. Every method had the same flaw. It could find gas where the gas was thick, or along one narrow line, or where it happened to be hot enough to shine. None could sweep the whole space and weigh what was actually there. The missing matter stayed missing, not because it was truly gone, but because it was too faint and too far flung for any light we knew how to use. The problem was never the scientists. It was the gas. It had a genius for giving back almost nothing. Almost nothing by every measure that counted, because of what it was made of and how thinly it was spread. Take a box of empty space, 3 feet on each side, somewhere out between the galaxies. Count the particles inside. You'll find fewer than 10. Hold that for a second. The air in front of your face, in a box that size, holds a number so large you couldn't write it out in an afternoon. Trillions upon trillions. Out between the galaxies, in the same size box, you get a handful of particles. Fewer than 10. That is the emptiest emptiness most of us will ever try to picture, and it goes on for distances that have no meaning on a human scale. Now you start to see the problem. To make light you can catch easily, you usually need matter packed together, bumping and crowding and burning. Stars do it. Hot, dense gas does it. But this gas isn't packed. It's the opposite. It's smeared so thin that its particles almost never meet. A particle can drift for a stretch you couldn't walk in 1,000 lifetimes before it touches another. Thin gas like that barely glows. There's nothing to make it shine. And what little light it does give off is spread across distances so vast that by the time it reaches us, it's fainter than the faint background of space itself. You point a telescope at it and you're really looking at nothing, or close enough to nothing that no instrument can tell the difference. There's a second trick the gas plays. Most of it isn't cold and it isn't blazing hot. It sits in a middle range, warm by the standards of space, hundreds of thousands of degrees, sometimes more. Scientists have a name for it. The warm hot gas between galaxies. And that middle temperature is the worst possible state for being seen. Too cool to pour out strong X-rays the way the hottest cluster gas does. Too hot and too thin to show up the gentle way cold gas does. It falls into a gap, a blind spot, between the methods we have. So picture the trap. The matter is real. It's everywhere. But it's too thin to glow, too spread out to catch what glow there is, and stuck at a temperature that hides it from both ends of our vision. Every quality that makes it hard to see comes from the same source. There's so much space and so little stuff in it. This is why the missing matter stayed missing. Not because anyone looked in the wrong place. People looked in exactly the right place. They looked at the dark between the galaxies, where the gas truly was, and the gas gave them nothing they could measure across the whole of it. It's a humbling thing to sit with. We tend to think seeing is the easy part and understanding is the hard part. Here it was backwards. Scientists understood the gas should be there. The early universe demanded it. The math was firm. The one thing they couldn't do was the simplest thing of all. Look at it. Weigh it. Say how much. You can't solve this with a better telescope of the usual kind. A bigger lens just gathers more of a glow that was never there. The gas won't shine for you no matter how long you stare. But there was another way to find out where the matter should be, without ever seeing it. You could build the universe inside a computer, and watch where everything went. So, they built universes inside machines. You take everything you know about how matter behaves, gravity, the push of dark energy, the pull of dark matter, the way gas heats and cools and flows. You write it all into a program. Then you fill a virtual space with matter spread almost perfectly smooth, the way the real universe started, and you let the clock run. What happens next, every time, is one of the strangest results in modern science. The smooth matter does not stay smooth. Gravity finds the tiny lumps, the places where there's a hair more material than average, and it pulls. Those lumps grow. They draw in matter from around them, and the space between them empties out to feed them. Run the clock far enough, and the matter has arranged itself into a shape, not a scatter, not an even spread, a web. Long threads of matter stretch across the simulated space, thin and bright with gas. Where the threads cross, matter piles into dense knots, and those knots are where galaxies and clusters form. Between the threads, huge rounded voids open up, nearly empty, the loneliest places in the model. The whole thing looks like a network, or a nervous system, or the inside of a sponge. Scientists call it the cosmic web. And here's what mattered for the missing baryons. In the simulation, you can see exactly where the ordinary matter ends up. Most of it does not end up in the galaxies. Most of it ends up in the threads. Strung along those vast filaments between the bright knots in a thin, warm haze is the bulk of the ordinary matter in the model universe. That was the prediction. The missing gas isn't truly missing. It's draped along the cosmic web, in the filaments, between the galaxies, exactly where it's hardest to see. The simulations have been saying so for years. Different teams, different machines, different methods, all producing the same picture. A web of gas with the galaxies as glowing beads on the threads, and most of the ordinary matter spread thin in the strands between. It's a beautiful answer. It explains the missing half cleanly. It even predicts roughly how much should be where. And for a long time, that was exactly the trouble with it. Because a simulation is not the universe. It's our best guess about the universe, dressed up in numbers and set in motion. It can be wrong. It has been wrong before. A model that produces a convincing picture has not proven the picture is real. It has only shown what follows from the rules you fed it. If you misjudge the rules, the web in the machine could be a beautiful mistake. So scientists were left in a strange spot. They had a firm number for how much ordinary matter the universe made. They had a clear prediction for where it should be hiding. The two even agreed. But agreement on paper is not proof. The real gas, the actual haze along the actual filaments, had never been weighed across the broad universe. Nobody had pointed at the threads of the cosmic web and measured what was there. The model said the matter was in the web. The sky refused to confirm it. And without confirmation, the missing baryon problem stayed open, a gap between what the theory demanded and what anyone had ever seen. To close it, you couldn't lean on the simulation. You had to catch the real gas in the act. You needed something to pass through the filaments and report back, honestly, how much matter it crossed. That something was already on its way. It had been traveling for billions of years, and it would arrive in a flash. On a quiet night, a radio dish on Earth catches a pulse that lasts about 1,000th of a second, and then is gone. That's it. A single brief flash of radio waves over almost before any instrument can register it. Blink, and it's done. But in that sliver of time, the dish has caught one of the most violent signals in the universe. These flashes have a name: fast radio bursts. And the word fast does not do them justice. A burst is over in a few thousandths of a second, sometimes less. In that flicker, it can release as much energy as the sun pours out in days, and in some cases far more. All of it dumped into radio waves, the same band of light that carries music to your car, except packed into a pulse so short and so strong, it crosses the entire universe and still arrives loud enough to catch. People only started noticing them recently. Less than 2 decades ago, someone sifting through old radio records found a single, strange spike. A burst that had come and gone years before and slipped past unexamined. At first, no one knew what to make of it. One flash could be anything. A glitch, a passing satellite, some local interference dressed up as a cosmic event. Then, the dishes caught more, and more. The bursts kept coming, from all over the sky, with no pattern anyone could read. By now they've been seen around 1,000 times, and the count climbs as the instruments improve. They arrive at all hours, from every direction, brief and bright and gone. Most of them never repeat. A flash fires once from some point in the deep sky, and is never heard from again, which makes them maddening to study. You can't plan to watch one. You can't aim your best instrument and wait. You catch it by chance, after it's already happening, or you miss it entirely. And they come from far. This was the part that turned a curiosity into a tool. When scientists worked out the distances, the flashes weren't going off nearby. They were erupting in other galaxies, across stretches of space so wide the light had been traveling for millions of years, and in the deepest cases, for billions. Sit with that. A flash leaves some distant galaxy. It crosses the entire span between that galaxy and ours, through every thread and void of the cosmic web, through all that thin, warm gas no telescope could weigh. The journey takes longer than the Earth has existed. And at the end of it, the pulse falls onto a dish on our small planet and registers for 1,000th of a second. For a while, the bursts were a pure mystery, a question with no answer. What could be powerful enough to send a signal across the whole universe in a single flick? What kind of object screams that loud and then goes silent? But while everyone argued over what made the bursts, a few people noticed something else. It almost didn't matter what made them. What mattered was the trip. Every one of these flashes had just crossed billions of light years of the exact space that hid the missing matter. Each pulse had passed straight through the cosmic web on its way to us. If the gas left a mark on that pulse, any mark at all, then the bursts weren't only a mystery to solve. They were a message, carrying a record of everything they'd touched. The first job was to figure out what could possibly throw a flash that bright. And the answer pointed to a kind of star so extreme, it barely counts as a star at all. When a giant star dies, its core can collapse into a ball the size of a city and heavier than the sun. That's a neutron star. The collapse squeezes its atoms until they cave in, and what's left is almost pure neutrons, packed to a density that breaks the imagination. A single spoonful would weigh about as much as a mountain. Neutron stars are already among the strangest things in the universe, and they're common enough that the galaxy is littered with them. Now take one of those and wrap it in a magnetic field beyond anything else known to exist. That's a magnetar. The magnetism around a magnetar is so strong, it would scramble the matter in your body from a distance no human will ever survive to test. It is the most powerful magnetic field in the universe, draped over a city-sized corpse of a star that spins and shudders and sometimes cracks. When a magnetar convulses, it can unleash a burst of energy that staggers belief. And this is the leading suspect for the fast radio bursts. The case grew strong when a magnetar inside our own galaxy let out a radio burst of its own, weaker than the distant ones, but clearly the same kind of event, caught by instruments that could see exactly where it came from. For the first time, a flash had a face. A magnetar had fired, and the dishes had caught it in the act. So that's the leading idea. Out in distant galaxies, magnetars are convulsing, and each convulsion throws a flash of radio waves across the universe. It fits a lot of the evidence. It explains the power. It explains the speed, but it would be dishonest to call the case closed. The bursts don't all behave the same way. Some repeat, firing again and again from the same spot, which is hard to square with a single catastrophic event. Most never repeat at all. There may be more than one kind of burst, made by more than one kind of object, lumped together because they all look like a brief radio flash from far away. The origin of fast radio bursts is still, in honest terms, an open mystery. Magnetars are the front runner, not the verdict. And here is the strange turn in the story. For the search that mattered most, it didn't matter who was right. That's worth slowing down on. Normally in science, you want to know what you're looking at. You want the source pinned down before you trust the signal. But the scientists hunting the missing matter realized they could use the bursts without solving them. They didn't need to know what made the flash. They needed the flash itself, and they needed it to have crossed a long stretch of the universe to reach us. Because the burst leaves its source clean. A sharp pulse of radio waves, all its different wavelengths starting out together, in step, in a single tight flick. Whatever a magnetar is or isn't, the pulse it throws begins as a clean signal. What happens to that clean signal on the long road home is the whole point. The journey leaves its fingerprints. By the time the pulse reaches Earth, it is no longer pristine. The gas it crossed has touched it, gently, invisibly, in a way the dishes can read with great precision. The mystery of the source could wait. The bursts had already done the one thing no telescope could. They had travelled through the missing matter, every last thread of it, and they had kept a record. The trick was learning to read that record. And it came down to a single subtle effect that happens to light when it crosses thin gas. The flash leaves its source all at once, every colour of radio waves starting the race together. They do not finish together. When a pulse of radio waves crosses thin gas, something happens that sounds small and turns out to be everything. The gas slows the waves down. Not by much, and not all of them by the same amount. The longer, lower waves get held back a little more than the shorter, higher ones. So a signal that started as one tight flash arrives, smeared out, with the high notes landing first and the low notes trailing behind. There's a plain version of this you already know. White light bends through a prism and fans into a rainbow, because different colours travel a touch differently through the glass. The gas between galaxies does something like that to a radio burst. It fans the flash out in time, stretching a pulse that began as a single instant into a brief downward slide, high to low. Scientists call this stretching dispersion, and the size of the stretch is the key to the whole story. Here is the part that turns it from a curiosity into a measuring tool. The amount of stretch depends on how much gas the pulse crossed. A flash that travelled through a lot of matter comes out badly smeared, the low notes lagging far behind the high. A flash that crossed less matter arrives almost crisp. The delay between the first wave and the last is a direct readout of everything the pulse passed through. So measure the stretch, and you've counted the matter. Every charged particle along the entire path leaves its tiny mark on the timing. Add up the marks, and the smear in a single flash tells you how much stuff stood between you and a galaxy billions of light years away. This is the effect that breaks the deadlock. The missing matter was invisible because it wouldn't shine, but it doesn't have to shine for this to work. It only has to be in the way. The gas can be as thin and cold and quiet as it likes. As long as a radio burst passes through it, the gas drags on the waves, and the drag gets recorded in the timing, whether the gas glows or not. Think about what that means after all those years of straining for a faint glow. The whole problem had been that the gas gave off almost nothing to see. Now that didn't matter. You weren't asking the gas to send you light anymore. You were sending light through the gas and reading the bill. And the bill came written into the shape of the flash, precise and unavoidable. A team put it simply. The bursts act like flashlights shining through fog. You can't see the fog directly. It's too thin, too faint, but shine a beam across it and measure how the beam comes out the other side, and you can weigh the fog you could never see. The flash is the flashlight. The cosmic web is the fog, and the stretch in the signal is the measurement. There's a catch, and it's a big one, and the scientists knew it from the start. The smear in a burst tells you the total matter along the path, but the path runs through more than the open space between galaxies. It also runs through the burst's own home galaxy on the way out, and through our galaxy on the way in. Those near pieces leave their marks too, mixed into the same number. So a raw burst gives you a total, not an answer. To find the gas in the web, you have to know how far the flash came, and you have to peel away the matter near both ends. And for that, one number from one flash was never going to be enough. An ordinary star would be useless for this, and the reason is worth seeing. A star shines steadily. Its light pours out hour after hour, year after year, with no sharp beginning. And dispersion only shows itself if the signal starts as a clean, single instant. You measure the stretch by timing how the high notes arrive ahead of the low ones. But if the source never stops shining, there are no distinct notes to time. The early light and the late light blur together into one steady glow. The fingerprint is there, smeared into the stream, impossible to pull back out. That's why this took a fast radio burst, and not the light of a star or a galaxy. The burst is perfect for the job in 3 exact ways, and it has to be all 3 at once. It has to be brief. A flash that begins and ends in 1,000th of a second gives you a sharp starting gun. You know all the waves left together, so any spreading you see was added on the road. The shorter the flash, the finer the measurement. It has to be bright. The signal has to survive a trip across billions of light years and still land hard enough to read. A faint flicker would drown in the noise of space. A fast radio burst is one of the few things violent enough to cross the whole universe and arrive loud. And it has to be radio. The stretching is strong for long, low waves, the radio band, and almost nothing for the kind of light your eyes use. Visible light barely disperses across these distances. Radio waves fan out clearly. The universe happened to be firing signals in exactly the band where the gas leaves its deepest mark. Put those three together, and you have a near miracle of a tool. A flash brief enough to time, strong enough to cross the cosmos, in the one kind of light that records the gas. Nobody designed it. Magnetars or whatever throws the bursts were never trying to help us weigh the universe. The signal just happens to carry the measurement we needed. Free, written in by the gas itself. But one burst, on its own, still can't finish the job. Remember the catch. The stretch in a single flash gives you the total matter along its whole path, end to end. Buried in that total is the gas of the burst's home galaxy, and the gas of our galaxy, and the long stretch of cosmic web between, all added into one number. From a lone flash, you can't tell which part is which. There's a deeper problem too. Even if you could clean up one burst, one path is one thread through the universe. It tells you about the gas along that single line, and nothing about the vast space to either side. It's the old quasar trouble all over again. A single drop does not measure the storm. The way out is not a better flash, it's more of them. Dozens of bursts, from galaxies scattered across the sky, near ones and far ones, each crossing a different slice of the cosmic web. Line them up, near to far, and a pattern appears that no single flash could show. The farther the flash came, the more web it crossed, and the more its signal should stretch. But none of it works unless you know one thing for each burst: how far it came. And a flash, by itself, does not announce its distance. To learn that, scientists had to do something far harder than catching the burst. They had to find its home. Catching a burst is one thing. Knowing where it came from is far harder. A flash lasts 1,000th of a second. In that blink, you have to not only record it, but pin down the exact patch of sky it came from, precisely enough to find the single galaxy that fired it. Miss by a little, and you're looking at a smudge of sky with dozens of galaxies in it, any one of which could be the source. Then the burst is gone, and it may never fire again. For years, this was the wall. The early instruments could tell a burst had happened, and roughly which direction, but not finely enough to name the home galaxy. And without the home galaxy, you can't get the distance. Without the distance, the stretch in the signal is just a number with no scale. You know the flash crossed a lot of gas. You don't know how much space that gas was spread across, so you can't say how thick it was. The fix came from spreading the dishes out. Instead of one radio telescope, you build an array, many dishes working as a team, set far apart from one another. When a burst arrives, it hits the different dishes at very slightly different moments, and it lands with subtle differences across them. By comparing those tiny differences, the array can triangulate the flash, narrowing its origin from a vague patch to a sharp point, tight enough to land on a single galaxy. Do that, and everything opens up. Once you have the host galaxy, you can turn ordinary telescopes on it, the kind that read visible light and measure its distance the standard way. Now the burst has a home and a range. You know how far the flash travelled, you know the length of the road, and with the distance in hand, you can finally take the burst apart. The total stretch splits into pieces you can reason about. There's the gas of the home galaxy near the start. There's the gas of our own galaxy near the end, which scientists can map and subtract because it's close and well studied. And in the middle, the long haul, there's the gas of the cosmic web, the part that had been missing all along. This is painstaking work, and every localized burst is a small victory. You wait for a flash you cannot predict. You catch it across an array of dishes. You triangulate the patch of sky. You find the host galaxy. You measure its distance. You subtract the near gas at both ends. And what's left is one clean reading of the matter in the open universe, along one thread, at one known distance. One reading isn't an answer, but the readings add up. Catch enough bursts from galaxies near and far, and each one gives a clean measurement along its own path. Some flashes come from close by, crossing only a little web. Some come from much farther, crossing a great deal. Each lands a single honest dot on a graph. Distance across the bottom. The stretch in the signal up the side. You can see where this is going. If the gas really fills the space between galaxies, then the farther a flash comes, the more gas it crosses, and the more its signal should stretch in a steady, predictable climb. The dots shouldn't scatter at random. They should line up. The slope of that line would be the thing nobody had ever measured. The amount of ordinary matter spread through the open universe. For a long time, there weren't enough dots to tell. A handful of bursts gave a hint of a trend, and no more. To draw the line with confidence, scientists needed a real haul of localized flashes, reaching as deep into the universe as they could go. So the chase was on for distance, and the deeper they reached, the more gas piled into each signal, until one flash arrived from so far away it set a record. One of the flashes in the hunt came from about 9 billion light years away. Let that distance settle. The light left its galaxy 9 billion years ago. The Earth did not exist. The Sun did not exist. The cloud that would one day collapse into our solar system had not yet gathered. That flash had been crossing open space for twice the age of our planet before it reached a dish on the ground, and registered for 1,000th of a second. It was the most distant fast radio burst anyone had ever caught, and distance in this hunt was the whole prize. Here's why the far ones matter so much. A nearby flash crosses only a short stretch of the cosmic web, so it picks up only a little of the gas. Its signal stretches just a bit, and that small stretch is easily muddied by the gas near the ends, the home galaxy and ours. The near bursts are useful, but they're noisy. They don't reach far enough into the open universe to say much about it. A distant flash is different. It plows through an enormous length of the web. It crosses thread after thread, void after void, billions of light years of the thin, warm gas. All of that piles into the stretch of its signal. The deeper the flash comes from, the more the open universe dominates the reading, and the smaller the muddle from the two ends becomes. The far bursts are where the missing matter shouts loudest. So a record-breaking flash from 9 billion light years out is not just a trophy. It's the strongest single probe in the whole set. A beam that crossed more of the hidden gas than any other, carrying the clearest record of the open universe back to us. And the far ones did something else. They stretched the graph, with bursts reaching from nearby galaxies out to the very edge of what the instruments could catch. The dots now spanned a huge range of distances. Close flashes low on the chart, distant flashes high, and the deepest one, from 9 billion light years, anchoring the far end, pulling the line out to its full length. This is what scientists have been missing. Not one perfect measurement, but a spread of them, from near to staggeringly far, enough to see whether the dots truly lined up the way the cosmic web predicted. A single distant burst proves little. A whole set of them, climbing steadily from the closed galaxies to the most distant flash on record, is a different kind of evidence. It's a trend. And a trend you can trust. It's worth pausing on how unlikely this all is. To weigh the most elusive matter in the universe, scientists are leaning on flashes thrown by dying stars in galaxies billions of light years away. Flashes that fire without warning, last 1,000th of a second, and may never come again. They catch them by luck and a web of dishes. They trace each one home. They read the gas in the stretch of the signal. And the farthest flashes, the ones that cross the most space, turn out to carry the most truth. There's something almost unbearable about the scale of it. A flash leaves a galaxy when the universe is young. It travels for 9 billion years through the exact dark that hid the missing matter. The whole time, the thin gas of the cosmic web is quietly writing itself into the shape of that pulse. And at the end, in a flicker too short to notice, it delivers its message to the one species that had been trying to read it. With the far bursts in hand and the close ones filling the gaps, the scientists finally had what they needed. Enough flashes, across enough distance to draw the line and read its slope. And when they read it, the missing half of the universe finally had an address. About 3/4 of the universe's ordinary matter is floating in the space between the galaxies. That's the answer. After more than 20 years, that's where the missing half was hiding. Not in some exotic form. Not in a place no one had guessed. In the thin, warm gas strung across the cosmic web, exactly where the simulations had said, and now, for the first time, actually weighed. The scientists ran the numbers from their set of localized bursts, and the split came out clear. Roughly 76 parts in 100 of the ordinary matter sits in the open space between galaxies, the intergalactic gas. Around 15 parts sits in the great halos of thin material that surround galaxies. And only the small remainder, less than 1/10, sits inside the galaxies themselves, in the stars and planets and cold clouds, the only part we could ever easily see. Read that split again, because it rewrites the picture most of us carry. The galaxies, with all their stars, hold the smallest share. The bright universe we photograph and admire is the leftover. The vast majority of ordinary matter never made it into a galaxy at all. It's out in the dark, in the gas between, in the part of the sky that looks like nothing. This is what closes the missing baryon problem. Not a guess, not a simulation. A measurement, drawn from real flashes that really cross that gas. One scientist on the work put it plainly. The question was never whether the matter existed. The early universe guaranteed it did. The question was always where. And now there's an answer. 3/4 of it is floating between the galaxies, in the web. It's worth being honest about what kind of victory this is. It isn't a shock that overturns physics. In a way, it's the opposite. The matter turned up almost exactly where the leading theory had placed it. The simulations were right. The early universe math was right. The strange part isn't that the answer is bizarre. The strange part is that something so ordinary, so central, so much of what we're made of, could stay hidden for so long and take flashes from the far side of the universe to finally pin down, sit with the scale of what was found. This is not a trace. It's not a footnote of leftover gas. It is most of the ordinary matter in existence, more than all the stars and planets and visible clouds combined. Several times over, all of it spread so thin and so wide that every method we had stared straight through it. The majority of the touchable universe was simply somewhere we couldn't look, until now. If this is the first you're hearing that most of the ordinary universe sits outside the galaxies, you're not alone, and it's the kind of thing worth following. Consider subscribing, and we'll keep going, because finding the matter is not the end of the story. It's the start of a stranger one. An address is not a picture. Knowing that 3/4 of ordinary matter lives between galaxies tells you it's there. It doesn't yet tell you what it looks like, how it's arranged, or how it got out there in the first place. And the same flashes that found the matter can do more than count it. Each burst measures the gas along its own particular path. Gather enough of those paths, crossing the sky in every direction, and you can begin to do something no one has ever done. You can map the hidden matter. Not just weigh it, but chart where it runs thick and where it thins out. The first rough version of that map already exists, and it shows a universe that looks nothing like the scatter of glowing dots we grew up calling space. For the first time, scientists could chart where the ordinary matter runs across the broad universe, instead of just adding up how much of it there was. This is the leap from a number to a map. Each localized burst is a single thread drilled through the cosmos, and along that thread, the stretch in the signal records how much gas the flash crossed. One thread tells you about one line, but the scientists now had a spread of threads, reaching in many directions to many distances. Lay them side by side, and the threads begin to sketch a structure. What emerges is a measurement of how ordinary matter is spread through the cosmic web. Not the simulated web in a machine, the real one. For the first time, the thin gas of the open universe had been weighed across a real stretch of sky, and the picture matched the prediction. The matter is not even. It's not scattered at random. It clumps along the threads and thins out in the gaps, just as the model had promised for years. That agreement matters more than it might sound. Up to now, the cosmic web was a thing simulations produced and telescopes hinted at. The bright knots, the galaxies, we could always see. But the threads between them, the filaments of thin gas that are supposed to hold the whole structure together, had never been weighed across the open universe. They were the connective tissue of the cosmos, predicted but unconfirmed. Now the flashes had touched them and brought back a number. The web was no longer just a beautiful output of a program. It was something we had reached out and weighed. And the scientists are blunt that this is only a first sketch. The map is coarse. It's drawn from a set of flashes that, on the scale of the whole sky, is still small. Think of it as the first faint outline of a continent, drawn by a handful of ships crossing a vast ocean, each reporting the depths along its own narrow route. You can tell there's land. You can see the rough shape. You can't yet read the rivers and the hills, but the method is proven, and that's the real prize. The hard part was never going to be drawing a perfect map on the first try. The hard part was showing it could be done at all, that flashes from dying stars could be turned into a survey of the most invisible matter in the universe. That part is done. The principle holds. Every new burst from here on adds another thread, sharpens another stretch of the outline, fills in another piece of the dark. There's a quiet reversal buried in all of this, and it's easy to miss. For all of history, we mapped the universe by its light. We charted the stars we could see, the galaxies that shine, the bright things. The dark between was just background, the empty stage the bright things stood on. Now that's inverted. The flashes ignore the bright things almost entirely. What they measure is the dark. They map the stage, not the actors. And the stage, it turns out, holds most of the matter. So we've started to draw a map of the part of the universe we were never able to see. A map of the gas, the threads, the hidden bulk of ordinary matter, sketched by flashes that crossed it on their way to us. It's rough. It will get better. Every dish now turning toward the sky is adding to it. And as that map fills in, it forces a question that's been building under everything. If most of the ordinary matter is out in the web, and only a sliver sits in the galaxies, then the picture of the universe we grew up with has the emphasis exactly backwards. The galaxies were never the main event. They were the bright exceptions. The real universe, the one that holds most of the matter, is the thing we've been treating as empty. Go outside on a dark night and look up, and almost everything you call the universe is a lie of emphasis. Not a lie about what's there, The stars are real. The galaxies are real. But they fool you about where the matter is. Your eye is drawn to the bright points because they shine, and you naturally assume that's where the substance is. That the universe is basically a collection of glowing things floating in empty black. That picture is upside down. The measurement makes it plain. Of all the ordinary matter in the universe, the galaxies hold the smallest part. Less than a tenth sits inside them, in the stars and worlds and cold gas. The rest, more than 9/10, is outside, most of it strung across the open space between, in the thin, warm gas of the web. The bright things you can see are the rounding error. The dark you ignore is the main body. Turn that over and it gets stranger. Everything humans have ever known by sight, every star our ancestors named, every galaxy in every photograph, all of it belongs to that thin minority of ordinary matter that happened to fall into a galaxy and light up. We built our whole picture of the cosmos from the exception. We mistook the glowing few for the substance of everything, because the glowing few were all we could see. And the dark majority isn't passive. This is the part that unsettles the scientists. The gas in the web isn't just sitting there as filler between the interesting bits. It's the reservoir. The galaxies formed from it, pulling material out of the web to make their stars. They feed on it. They blow matter back into it. The thin gas between the galaxies is not the leftover. In a real sense, it's the source, and the galaxies are temporary bright spots that condensed out of it. So the shape of the universe is not what your eye reports. The honest shape is the web. Long threads of thin gas, stretching across distances that crush the imagination, with galaxies strung along them like dew, caught on a strand. Between the threads, immense rounded voids, almost truly empty. Most of the ordinary matter lives in the threads, in the dark, in the part that gives off nothing you can see. The bright knots are real, but they are not the structure. They're decoration on it. This is the reframe the missing matter forces. The question that started all this was simple. Where is the other half of the ordinary matter? And the answer turned out to be bigger than a location. The answer rearranges the whole picture. The matter wasn't missing because it was rare or strange. It was missing because it sits in the part of the universe we'd quietly decided was empty. We were looking past most of the universe to stare at the bright flecks inside it. And finding it raises a harder question than the one we started with. We know now that most of the ordinary matter is out in the web. But how did it get there? The simulations say galaxies are born from that gas, pulling it inward. So why is most of the matter outside the galaxies, not inside them? Something must have driven it back out, into the dark, against the pull of gravity, and spread it across the threads. That something turns out to be violent. The gas didn't drift gently into the web. It was thrown there, by forces inside the galaxies powerful enough to blast matter clear across the void. The same galaxies that gather matter also expel it, in outbursts that decide where everything ends up. And the most powerful of those engines sits at the very center of things, in the dark hearts of the galaxies themselves. Picture the universe drained of its light, so only the matter is left to see. The stars go dark. The galaxies stop shining. All that remains is the stuff itself, lit up by nothing, laid bare in its actual arrangement. And what you'd see is not a scatter of dots in a void. You'd see a structure, vast and intricate, filling all of space. Long threads of matter run in every direction, stretching across distances that take light hundreds of millions of years to cross. The threads branch and cross and braid together. Where several of them meet, the matter piles up thick into dense knots, and those knots are the crowded places where galaxies gather by the thousands. Between the threads, the matter thins almost to nothing, opening into enormous rounded hollows, the voids. Some so empty, you could travel through one for ages and pass almost nothing at all. This is the cosmic web. It is the largest structure in the universe, and in a real sense, it is the only structure. Everything else hangs on it. It helps to shrink it down. Imagine a sponge, the kind in your kitchen, full of holes. The solid part of the sponge is the threads and knots, the matter. The holes are the voids. Now, blow that sponge up until a single one of its holes is wide enough to swallow whole clusters of galaxies, and you have the rough shape of the cosmos, matter clinging to walls and strands, emptiness ballooning in the gaps. For a long time, this web was something we mostly inferred. We could see the galaxies clustering, the bright knots where the threads crossed, because galaxies shine. But the threads themselves, the long filaments of thin gas that connect the knots and carry most of the ordinary matter, gave off almost nothing. We knew the knots were joined. We couldn't see what joined them. The connective strands were dark. That's what the flashes changed. By weighing the gas along their paths, the bursts started touching the threads directly, the parts between the galaxies, and confirming that the matter really does run along them the way the web demands. The skeleton we had only sketched is being filled in, strand by strand, by light that crossed it. And calling it a skeleton is more than a figure of speech. The web came first. In the early universe, the gas spread out along these threads under gravity before the galaxies fully formed. The galaxies grew at the crossing points, where the threads fed the matter. So the web isn't a pattern the galaxies happen to make. It's the frame they grew on. Pull the galaxies away and the frame remains, the deeper and older thing. There's a strange intimacy to it once you know it's there. The thread our own galaxy sits on runs off into the dark in both directions, joining us to other galaxies we'll never reach, through gas we can't see. We're a bright bead on one strand of an immense web, and most of that web is the dark gas between the beads. The structure is not out there, separate from us. We are hung inside it. So the true shape of the universe is settled, and it isn't the one your eye gives you. It's the web. Threads, knots, and voids, carrying the bulk of the ordinary matter in their thin gas. The galaxies are the lit points where the threads cross, but knowing the shape only sharpens the question of the stuff. What is this gas, really? This material that fills the threads and outweighs every star? Up close, it turns out to be almost nothing at all. If you scooped up a cup of the gas between galaxies and a cup of the air in your room, the room's air would hold trillions of times more matter. The intergalactic gas is the thinnest stuff there is. We touched this earlier with the count of particles in a box, but it's worth looking straight at what this material actually is, because it's the substance that holds most of the ordinary matter in the universe, and it is barely there. It's mostly hydrogen, the simplest, lightest element, the same gas that fuels stars. Some helium mixed in, a faint trace of everything else. And it's spread so thin that across the distances of the web, the particles drift alone, rarely meeting. By any human standard, a stretch of it is a perfect vacuum, emptier than anything we can make in a laboratory on Earth. It's also hot, and not in a way your body would ever feel. The gas sits at temperatures of hundreds of thousands of degrees, sometimes climbing into the millions. Scientists call it the warm hot gas between galaxies, and that heat is part of why it stayed hidden. We met this trap before. The gas is too hot to show itself the gentle way cold gas does, and too thin to blaze in X-rays the way the dense gas in galaxy clusters does. It falls into the gap between our methods and gives back almost nothing. But here is the thing that turns almost nothing into nearly everything. There is so much space. The threads of the web run for hundreds of millions of light years. The total volume of all that open space is so staggering that even gas this thin, multiplied across it, adds up to the largest share of ordinary matter in existence. A whisper of substance, spread across an ocean of distance, outweighing every solid thing combined. That's the paradox at the heart of the find. The most abundant ordinary matter in the universe is also the most diffuse. If you went looking for it expecting something grand, a great cloud, a wall of gas, you'd be disappointed. Up close, in any one spot, there's almost nothing to see. You'd swear you were in empty space. The matter only reveals itself in the sum, across distances no traveller could ever cross. It's a humbling kind of substance to be made mostly of. Not dense, not bright, not dramatic in any single place, just there, faintly, across an unimaginable span. The bulk of the touchable universe is this thin, warm haze, and you could stand in the middle of a thread of it and feel utterly alone in the dark. And it would be wrong to picture it as still. The gas isn't a calm fog settled over the universe. It moves. It flows along the threads, drawn by gravity toward the dense knots where galaxies feed. It gets heated and pushed and stirred. In places it's falling inward, sinking toward the galaxies. In other places it's rushing outward, blasted away from them. That last part is the real mystery now. Gravity pulls this gas toward the galaxies. Galaxies are born by drinking it in. So if everything is being pulled inward, why is most of the matter outside in the web, instead of locked up in the galaxies where gravity wants it? Something has been pushing back, hard, against the pull. Something inside the galaxies has been blowing this gas back out into the dark. Gravity spent billions of years pulling gas into the galaxies. Then the galaxies threw most of it back. This is the puzzle the measurement leaves on the table, and it's a sharp one. Galaxies form by gathering gas. Their gravity, helped by the unseen dark matter around them, reaches into the web and pulls the thin material inward, where it piles up, cools, and lights into stars. That's the story of how a galaxy is born. It drinks from the web. So you would expect the galaxies to be full and the web to be drained. Run the simple version in your head. Gravity gathers. The gas falls in. Over the long age of the universe, most of the matter should end up where gravity wants it, inside the galaxies, packed into stars and worlds. The web should be the empty leftover. The measurement says the opposite. Most of the ordinary matter is outside the galaxies, in the web, and only a sliver made it into the stars. Gravity had billions of years to pull the gas in, and somehow the gas mostly stayed out. The galaxies hold the smallest share of the very material they're built from. The only way that happens is if something fought the pull. Something inside the galaxies has been shoving gas back out, against gravity, across enormous distances, hard enough to spread it through the web and keep it there. Scientists have a plain name for this pushing. They call it feedback. The galaxies don't only gather matter, they expel it. And the new measurement shows the expelling must be powerful, because it won the contest. Most of the gas got blown back out and stayed out. That word, feedback, hides how violent the reality is. We're not talking about a gentle leak. To drive gas out of a galaxy and across the void, you need to push it free of the galaxy's own gravity, then keep pushing until it's spread through the web. That takes forces of a scale that's hard to hold in the mind. Explosions, jets, outflows that move at a fair fraction of the speed of light. The thin, warm gas in the threads didn't drift out there. It was thrown. And the measurement does more than say this happened. It says it happened efficiently. It happened. The split, with 3/4 of the matter out in the open space, tells the scientists that the galaxies are extraordinarily good at expelling their gas. The feedback isn't a minor effect trimming the edges. It's the dominant force deciding where ordinary matter ends up. The galaxies emptied themselves, and the Webb caught what they threw. This reframes a galaxy completely. We tend to think of a galaxy as a thing that holds matter, a great basin where stars collect. The truth is closer to a fountain. Matter pours in from the Webb, and matter blasts back out, and the blasting wins. A galaxy is less a container than a churning engine that takes in gas and hurls most of it back into the dark. So the missing matter wasn't lost or strange. It was exiled, driven out of the galaxies by something powerful enough to beat gravity across the cosmic distances, and scattered through the Webb where it had been hiding all along. Which leaves the obvious question, what is strong enough to do that? What lives inside a galaxy that can blow its own matter clear across the void? The first answer sits at the very center, in the darkest object a galaxy owns. At the heart of nearly every large galaxy sits a black hole, millions or billions of times heavier than the Sun. These are the supermassive black holes, and they are among the most extreme objects in existence. Our own galaxy has one at its center, a region where so much mass is crushed into so small a space that nothing, not even light, can climb back out. Most big galaxies have one. They sit in the core, silent for long stretches, and then they feed. You'd think a black hole would be the opposite of an engine that throws matter out. A black hole takes things in. It's the great swallower, the place where matter falls and never returns. How could it be the thing blasting gas across the void? The answer is in what happens just before the matter falls. Gas spiraling toward a supermassive black hole doesn't drop straight in. It piles into a flattened, whirling disk, circling closer and closer, and as it crowds together, it heats to a ferocity that beggars description. The infalling material near a feeding black hole becomes some of the brightest, most violent stuff in the universe, blazing across the whole spectrum of light. And not all of it falls in. The black hole is a messy eater. The chaos around it, the searing heat, the twisting magnetic fields, the sheer pressure of all that radiation flings a large share of the gas back outward before it can cross the point of no return. Some black holes launch narrow jets of matter from their poles, beams that scream out of the galaxy at nearly the speed of light, reaching distances that dwarf the galaxy itself. Others drive broad winds, vast outflows of gas pushed outward by the storm of energy at the center. So the swallower is also a blower. The same feeding that pulls matter toward the center heats and stirs the surroundings so violently that much of the gas gets hurled away instead, out of the core, out of the galaxy, into the Webb. A feeding supermassive black hole is one of the few engines in the universe powerful enough to drive gas clear across the void and keep it there. This is the leading explanation for the most powerful feedback. The new measurement of the missing matter fits it. To blow 3/4 of a galaxy's ordinary matter out into the Webb, you need a force on the scale of these central engines. The black holes, when they feed and roar, can clear a galaxy of its gas, beating gravity from the inside. There's a grim elegance to it. The darkest object a galaxy owns, the one place matter goes to vanish, turns out to be a major reason most of the matter ended up far away in the open. The black hole doesn't just devour. By devouring violently, it scatters. The thin gas of the cosmic web, the missing material we hunted for 20 years, is partly the exhaust of the monsters at the centers of galaxies. But black holes are not the only thing that throws matter into the dark. They are the most extreme engine, the one at the core. There is another force at work, spread all through the galaxy, going off again and again, every time a great star reaches the end of its life and tears itself apart. Every so often, a massive star runs out of fuel and destroys itself in an explosion that can briefly outshine its entire galaxy. This is a supernova. A star far heavier than the Sun burns through its fuel, loses the fight against its own gravity, and collapses in a fraction of a second. The collapse rebounds into a blast so violent, it scatters most of the star across space, sending out a shockwave that races outward for thousands of years. For a short while, that single dying star can shine brighter than all the billions of stars around it combined. One supernova is a staggering amount of energy poured into the gas around it. And the key thing is that supernovae are not rare on the scale of a galaxy. Massive stars live fast and die young, burning out in a few million years, a blink in cosmic time. So across a galaxy, somewhere, these explosions keep happening again and again over its whole long life. Each one slams energy into the surrounding gas and shoves it outward. That's the other great engine of feedback, where the supermassive black hole is a single monster at the center. The supernovae are spread all through the galaxy, going off wherever big stars die. Each blast heats the gas nearby and pushes it. Together, over time, they drive enormous outflows, lifting gas up and out of the galaxy and into the web. There's a deeper twist in the supernovae, and it changes how you should think about your own body. The explosion doesn't just push gas around, it makes a new matter. The heavy elements, the carbon in your cells, the oxygen you breathe, the iron in your blood, the calcium in your bones were forged inside massive stars and in the supernovae that tore them apart. The blast that throws gas into the web is also the blast that creates the elements life is built from and scatters them outward at the same time. So picture the cycle. A massive star lives and dies. Its supernova forges new elements and hurls them, along with the surrounding gas, out of the galaxy. That enriched gas joins the web, mixing into the thin, warm haze between the galaxies. The missing matter isn't just hydrogen left over from the beginning. Woven through it are the ashes of countless dead stars, the heavy elements they made in their final moments, blown out into the dark. Between the two engines, the picture of feedback comes together. The black holes at the centers drive the most powerful outflows, clearing gas from the cores. The supernovae, spread across the galaxies and firing through all of cosmic time, push gas out from everywhere else and seed it with new elements. Both fight gravity. Both throw matter into the web. Together, they are why most of the ordinary matter ended up outside the galaxies, in the open space, where it hid. The new measurement gives this a kind of confirmation. The fact that 3/4 of the matter is out in the web means these engines, the black holes, and the supernovae were powerful enough and frequent enough to win, to expel most of the gas and keep it expelled. The thin gas we finally weighed is the record of all that violence. The cooled exhaust of black holes and dying stars spread across the cosmos. And the gas isn't only blown out once and abandoned. It can fall back. The whole thing turns out to be a cycle, a balance, with gas flowing both ways. That balance has a quiet job. It decides whether a galaxy keeps making stars or chokes and goes dark. A galaxy lives or dies by a balance between two flows, gas falling in and gas blasting out. Both are always happening. Gravity keeps pulling fresh gas in from the web, feeding the galaxy, giving it the raw material to make new stars. At the same time, the engines inside, the black hole and the supernovae, keep blasting gas back out. The galaxy is caught between these two flows for its entire life, taking in and throwing out, and which one wins at any moment decides what the galaxy becomes. Scientists describe this with a comparison that fits it well. The galaxy works like a thermostat. When too much gas piles in and the galaxy starts forming stars too fast, the violence ramps up. More massive stars means more supernovae. A faster feeding center means a more active black hole. All that energy heats the gas and blows it outward, cutting off the supply, slowing the star making down. It's a self-correcting loop. Run too hot and the galaxy throws off the excess and cools itself. This is why the balance matters so much. Without the outflows, a galaxy would gather gas unchecked, blaze through it, and burn out fast in a frenzy of star formation. With too much outflow, it would empty itself completely and go dark, starved of material. The thermostat holds it in between, regulating the pace, letting a galaxy form stars steadily over billions of years instead of all at once. And the gas that gets blown out isn't necessarily gone for good. Some of it escapes far into the web and stays there. But some of it slows, stops, and falls back, drawn again by gravity, returning to the galaxy to perhaps form stars another day. The matter cycles, out and back, in a slow churn that runs across the whole age of the universe. The web isn't only a graveyard for expelled gas, it's also a reservoir the galaxies draw from and return to, over and over. The new measurement of the missing matter is a snapshot of where this balance has settled. 3/4 of the ordinary matter out in the web, only a small part locked in stars, tells the scientists that across cosmic history, the outflows have been strong. The thermostat runs hot. Galaxies have been efficient at expelling their gas and keeping most of it out. The split we measured is the long-run result of this churn, frozen into a single number we could finally read. There's something almost alive in the picture, though it's worth being careful with the word. A galaxy breathes. It draws gas in from the web, burns some into stars, and exhales the rest back into the dark, where it mixes, cools, and may someday be drawn in again. The thin gas between the galaxies is the air of this breathing, the shared medium that every galaxy takes from and gives back to. The web feeds the galaxies enrich the web, and the whole slow exchange shapes how the universe lights up over time. So, the missing matter was never just sitting in the dark, inert, and forgotten. It's part of a living cycle, the exhaust and the reservoir and the fuel all at once, flowing between the galaxies and the web across billions of years. Finding it didn't just fill a gap in an accounting sheet. It revealed the breathing of the cosmos, the great exchange of matter that decides where and when the universe makes its stars. And if all of this matter has been cycling in and out of the web for the whole age of the universe, then it raises a question that comes much closer to home. The atoms in your own body, where have they been? The answer reaches back into that dark gas, and it's stranger than it sounds. The iron in your blood and the oxygen in your lungs were made inside stars that died long before the Earth was born. Trace any atom in your body back far enough, and the story leads to the same places. The hydrogen goes all the way back to the beginning of the universe. But the heavier elements, the carbon, the oxygen, the iron, the calcium, were forged in the hearts of massive stars, and in the supernovae that tore those stars apart. Every heavy atom in you was cooked in a star and scattered when it died. This is true, and it's been known for a while. The new measurement adds a chapter to it that's stranger and more personal. Because when those stars died and scattered their elements, the explosions didn't gently sprinkle the new matter nearby. They blasted it out into the web, the same feedback that drove most of the ordinary matter into the dark. So the atoms that would one day become you didn't simply drift from a dead star into the cloud that made our solar system. Many of them were thrown out into the thin gas between galaxies first, into that warm haze, the missing matter, where they drifted in the dark for ages. Follow the path of a single atom of iron in your blood. It was forged in the death of a massive star. It was hurled out into the intergalactic gas, into the web, where it joined the thin, warm haze and drifted alone across distances and spans of time that crush the imagination. At some point, gravity drew that gas back inward, toward a galaxy, into a thread feeding a knot of the web. It fell back in. It mixed into a cloud, and eventually that cloud collapsed to make stars and planets, and a small part of it became the Earth. And a smaller part still became you. The matter you're made of has been to places you never will. It spent stretches of time, longer than the Earth has existed, as part of the missing matter. The thin gas in the dark between galaxies. The very material that physicists hunted for 20 years. The stuff that hid from every telescope is in your hands right now, gathered for a brief while into a body that can wonder where it's been. This is what the measurement does that no number on a chart can. It collapses the distance between you and the cosmic web. The missing matter is not a remote abstraction, some gas in a faraway dark that has nothing to do with your life. It's the same stock of ordinary matter your body is drawn from. You are a temporary arrangement of the web's material, briefly gathered into the rare bright minority that fell into a galaxy and lit up. And it isn't a one-time journey. The matter doesn't go out into the web once and then stay locked in a body forever. It cycles. It flows out and falls back. Again and again, across the age of the universe, your atoms are not at the end of their travels. They're passing through you, on loan from the Great Exchange, and one day, they'll move on. That cycle is the deepest thing the missing matter reveals. Not a static map of where the gas is, but a vast, slow churn that has been running since the universe was young, moving matter between the galaxies and the web, building bodies and stars, and then taking them apart again. Nothing in the universe stays where it's put. The matter is always on the move, out into the dark and back again. This is the long churn, and it runs across the entire history of the cosmos. The web feeds gas into galaxies. The galaxies forge stars and elements. The dying stars and feeding black holes blast their enriched gas back out into the web. Gravity slowly pulls some of it back in, and the cycle turns again. Out and in, enriched a little more each pass, over billions of years. The new measurement is a still photograph of a process that never stops. When the scientists found 3/4 of the ordinary matter out in the web, they weren't seeing a final resting place. They were seeing where the matter happens to be right now, at this moment in a cycle that has been running since the first galaxies formed and will keep running long after. The gas in the threads is in transit between one trip through a galaxy and the next. This recycling explains something the simple picture couldn't. If galaxies only ever gathered gas, they'd have used it up long ago, burned through their fuel in a furious early burst, and then gone dark. Many galaxies are still making stars, slowly, steadily, billions of years on. They can do that because the fuel keeps returning. Gas blown out into the web cools, falls back, and feeds a new round of star making. The web is the bank the galaxies draw on, again and again, to keep the lights on across cosmic time, and every trip changes the matter. Each time gas passes through a galaxy, The stars there forge a little more heavy material and scatter it back into the flow. So the web isn't just storing the same gas it started with. It's slowly being enriched, salted with the elements made in generation after generation of stars. The thin gas between the galaxies today carries the ashes of countless stellar lifetimes, mixed into the original hydrogen from the beginning. Step back, and the scale of it is almost too much to hold. This churn has been turning for most of the age of the universe. The matter in the web has cycled through galaxies, through stars, through explosions, through the dark, more times than anyone can count. The atoms didn't take one journey. They've been going around and around, building things and being torn apart and scattered and gathered again, in a slow rhythm that spans the life of the cosmos. And we only just learn to see it. For all of history, this entire cycle, the breathing of matter between the galaxies and the web, was invisible to us. We could see the galaxies, the bright endpoints. We couldn't see the gas that fed them or the gas they expelled. We watched the stars without knowing where their material came from or where it went. The whole great exchange, the engine of how the universe makes and remakes itself, ran in the dark, beyond our reach. Now a flash from a dying star, crossing that dark, has started to reveal it. We can weigh the gas in the threads. We can begin to see the cycle that builds galaxies and bodies and worlds. The missing matter wasn't a gap in a ledger. It was the hidden half of how the universe works. The part that does most of the moving. The part we've been blind to all along. And that the matter turned up exactly where the theory predicted, doing exactly what the simulation said it should, is its own kind of triumph. It means the violent, churning picture of the cosmos was right. For years, the most violent picture of how galaxies work lived only inside computers. Now it's been confirmed by light from the real universe. Remember where the prediction came from. Scientists built universes inside machines, fed them the rules, and watched. The simulations produced the cosmic web. They put most of the ordinary matter out in the threads, and they did that by including the violence, the feedback, the black holes, and supernovae blasting gas out of the galaxies. Without that violence in the model, the matter stayed locked in the galaxies and the result looked nothing like reality. With it, the simulated universe matched the real one. But a simulation that matches what you already see isn't proof. We met this problem before. The web in the machine could have been a beautiful guess that happened to look right for the wrong reasons. The deep prediction, the one that mattered, was about the part we couldn't check. The simulation said most of the ordinary matter should be out in the open space between galaxies, blown there by feedback. Nobody had ever weighed that gas across the broad universe to find out if the models were right. The flashes weighed it, and the answer came back, matching the simulations. 3/4 of the ordinary matter out in the web, a small part in the galaxies, the split landing close to what the violent models had predicted for years. The measurement didn't overturn the picture, it confirmed it. The universe really does work the way the simulation said, with feedback strong enough to drive most of the matter out into the dark. This is a quieter kind of result than a shocking discovery, and in some ways a more powerful one. It means we understand something real about how galaxies live. The whole story, the gathering and the burning and the blasting out, the thermostat, the churn, isn't just a tale that fits the bright parts we can see. It's been checked against the dark parts, the hidden gas, the missing matter, and it holds. The model passed a test. It could have failed. And it could have failed. That's what makes it matter. If the scientists had weighed the gas and found most of the ordinary matter still locked inside the galaxies, the violent picture would have been in trouble. The feedback would have to be weaker than the models claimed, and the whole story of how galaxies regulate themselves would need rebuilding. The measurement was a real test, with a real way to come out wrong. It came out right. So the find does double duty. It solves the missing baryon problem, telling us where the matter is, and it confirms the violent model of galaxy life, telling us how the matter got there. 2 questions, 1 measurement. The gas is in the web, and it's in the web because the galaxies threw it there, exactly as the simulations have been insisting. There's a lesson buried in this about how science closes in on the truth. The simulations made a bold claim about a thing we couldn't see. For years it sat as a prediction, convincing but unconfirmed. Then a new kind of signal arrived, the flashes, and gave us a way to check the claim against the real universe. And the universe agreed. That's the pattern of a field maturing, moving a grand idea from the screen of a computer to a measurement of the actual sky. But the flashes don't stop at confirming what we already suspected. The same signals that weighed the missing matter can be turned on questions far beyond it. Questions about the lightest particles in existence, and the shape of the whole cosmos. The same flashes that found the missing matter can be used to weigh one of the lightest things in the universe. There's a particle called the neutrino. It's almost nothing, far lighter than the particles in an atom, so light that for a long time scientists thought it might have no weight at all. Neutrinos pour through the universe in unimaginable numbers. Trillions are passing through your body every second. From the sun, from distant explosions, from the early universe itself, and they slip through you and the whole Earth without touching a thing. They are the closest matter comes to being a ghost. We know neutrinos have some weight, but not how much. Pinning down the mass of the neutrino is one of the great open problems in physics, and it's stubborn because the particle barely interacts with anything. You can't put a neutrino on a scale, you can't trap it. Its weight is one of the most wanted numbers in science, and it has resisted every direct attempt to measure it. Here is where the flashes come back in. Neutrinos, light as they are, still have a faint gravitational effect, and across the whole universe, in their vast numbers, that effect shapes how matter clumps into the cosmic web. Heavier neutrinos would smooth the web out a little, blurring the fine structure. Lighter ones would let it clump more sharply. So the exact texture of the cosmic web, how the matter is spread, carries a clue to the neutrino's mass. And the flashes measure the texture of the web. By weighing the gas along many paths, the bursts map how the ordinary matter is distributed, how it clumps and thins across the cosmos. As that map sharpens, it can be read for the subtle fingerprint the neutrinos leave on the structure. The same signals that solved the missing baryon problem could help corner one of the lightest particles in existence. A flash from a dying star, used to weigh a ghost. That's not the only deeper question the flashes can reach. They can also be turned on the shape and history of the whole universe. By measuring how much gas lies along paths of different distances, the bursts probe how space itself has stretched over cosmic time, which feeds into some of the biggest open puzzles in cosmology, including a stubborn disagreement over exactly how fast the universe is expanding. The flashes give scientists a fresh, independent way to attack problems that have resisted older methods. This is what it means for a tool to be more powerful than the problem it was built for. The bursts were turned loose on the missing matter and they solved it. But the same trick, weighing what a flash crosses, turns out to be a key that fits other locks. The mass of the neutrino, the expansion of the universe, the deep structure of the cosmos, all of it written into how a flash of radio waves comes out the far side of the dark. And the scientists are clear that this is just the opening. The measurements so far rest on a modest haul of flashes. The real power comes when the count climbs, when the dishes start catching not dozens of bursts, but thousands, and that flood is coming. New instruments are being built right now whose whole purpose is to catch these flashes by the thousand, and they will turn a rough first sketch into a detailed map of the hidden universe. Right now, scientists catch these flashes a few at a time. Soon, they'll catch thousands. The measurements that found the missing matter rested on a set of flashes you could count without running out of patience. Dozens of bursts, each one localized through painstaking work, each a hard-won dot on a graph. That was enough to solve the problem, to weigh the gas and confirm the web. But it's a thin sample, a handful of threads drilled through an enormous universe. The map drawn from it is a coarse first outline. That's about to change, and not slowly. A new generation of radio telescopes is being built specifically to hunt these flashes. Instruments designed from the ground up to catch fast radio bursts and pin down where they come from. Where today's dishes snag bursts here and there, these new arrays are expected to detect them by the thousand, flash after flash, from every direction in the sky. Think about what that does to the map. Every burst is one thread through the cosmic web, one measurement of the gas along one path. A few dozen threads give you a rough sketch, the faint outline of a continent. Thousands of threads, crisscrossing the sky in every direction to every distance, give you something far closer to a real chart. The hidden gas, the missing matter, mapped in detail across the universe. The threads and knots and voids of the web, weighed and drawn, not guessed. The scientists describe this as the start of a golden age, and the phrase is earned. We've gone, in a short stretch of time, from not knowing where most of the ordinary matter was, to having a tool that can map it across the cosmos. And the tool is only getting sharper. Each new instrument multiplies the flashes, and each flash sharpens the picture. The trickle of bursts is about to become a flood, and the flood will fill in everything the trickle left blank. What that detailed map might show, no one fully knows yet, and that's the exciting part. With thousands of paths through the web, scientists could trace individual threads, watch how the gas flows between galaxies, see the outflows from feedback in finer detail, read the neutrino's fingerprint more clearly, pin down the expansion of the universe with a fresh tool. Questions that are barely approachable now become answerable when the flashes pour in. The find we've been following is not the end of a story. It's the first measurement in a field that's just opening up. There's something fitting about how this works. The universe is firing these flashes constantly, from dying stars and galaxies across all of space, whether or not anyone is listening. The signals have been crossing the dark forever, carrying their record of the gas, waiting to be read. We're only now building ears wide enough to catch them in bulk. The information was always streaming in. We're finally learning to gather it. So the missing matter was found, and that was the breakthrough. But it's also the doorway. Behind it is a whole way of seeing the universe that we've barely stepped into. A way of weighing the dark instead of just admiring the light. The flood of flashes is coming, and with it, the clearest view yet of the hidden bulk of the cosmos. And yet, for all that's about to be revealed, the discovery carries an unsettling lesson underneath the triumph. It took flashes from the far side of the universe to find something that was all around us, which means, for the whole of human history until now, we were blind to most of the ordinary universe. For thousands of years, humans looked up and thought they were seeing the universe. They were seeing a tenth of it. This is the uneasy thing under all the triumph, and it's worth facing plainly. Every star our ancestors named, every constellation, every galaxy in every photograph ever taken. All of it belongs to the small minority of ordinary matter that fell into a galaxy and lit up. The bright fraction. Less than 1/10 of the ordinary matter there is. We built our entire picture of the cosmos out of the part that happened to shine and called it the universe. The rest, the majority, was right there the whole time, not hidden in some far corner we hadn't reached. Spread through the space all around us, through the dark between the galaxies, in the thin, warm gas of the web. We looked straight at it, generation after generation, and saw nothing. It gave off no light our eyes or our instruments could catch, so we treated it as empty. We mistook the container for the contents, the dark for the absence of matter, when the dark held most of the matter. Sit with how recently this changed. For the entire span of human history, through every astronomer who ever lived, through the building of every great telescope, most of the ordinary universe stayed invisible. It took a new kind of signal, flashes from dying stars billions of light years away, caught only in the last stretch of years, to finally weigh what was always around us. We solved it almost in our own moment, after being blind to it for all the moments before. And here's the part that should give you pause. If most of the ordinary universe could hide from us in plain sight, behind nothing more than its own faintness, what else is out there that we still can't see? The missing matter wasn't exotic. It wasn't strange new physics. It was the most ordinary stuff there is. Hydrogen and helium, the plainest material in existence. And it eluded us completely until a few years ago. If the plain stuff could hide that well, the universe is clearly under no obligation to show us what it contains. This is the quiet dread the discovery leaves behind. Not fear of the gas itself, which is harmless, thinner than any vacuum. The unease is about us, about how much we miss, about how confidently we mistook a sliver for the whole. We are very good at seeing what shines. We are nearly helpless before what doesn't. And the universe, it turns out, keeps most of its ordinary matter in a form that doesn't shine. The missing matter is found now, and that's real progress. But the lesson it teaches outlasts the solution. It says our view of the cosmos has always been shaped by what we could detect, not by what's actually there. It says the bright universe we trusted was a small, biased sample. It says that being unable to see something is not the same as it not being there. A lesson the missing baryons taught at the scale of most of the ordinary matter in existence. And the ordinary matter is the part we finally caught. It's the easy case, the familiar stuff, hydrogen and helium that we understand. Beyond it sits the far larger darkness we haven't caught at all. The matter and the energy that make up almost the entire universe, and that we still cannot weigh with any flash. Everything we've talked about so far, all the matter, the galaxies and the gas and the web, is 5% of the universe. Hold that, after everything. The missing baryons, the cosmic web, the thin gas that outweighs every star. The whole great exchange of matter. All of it together is the ordinary matter. And the ordinary matter is about 5 parts in 100 of what's out there. The triumph we've been following, the solving of a 20-year mystery, was a triumph over a 20th of the universe. The other 95% is the larger dark, and we have barely touched it. About a quarter of the universe is dark matter, the unseen stuff whose gravity holds galaxies together and built the scaffolding the web hangs on. We know it's there only by its pull. It gives off no light at all, not faint light like the missing gas, but none. The flashes that weighed the ordinary matter can't weigh the dark matter directly. It stays beyond them. And most of the universe, more than 2/3 of everything, is dark energy, the strangest of all. It's the push driving the universe to expand faster and faster. stretching space wider every second. We don't know what it is. We have a number for how much it pushes, and almost nothing else. It is the dominant thing in the cosmos, the force shaping its whole future, and it's very nearly a complete mystery. So put the discovery in its true place. We found the missing half of the ordinary matter, and that was hard. And it took flashes from across the universe to do it. But the ordinary matter was the part we understood. It was the plain stuff, made of particles we know, behaving by rules we've worked out. The hard-won victory was over the familiar. The vast majority of the universe is still made of things we cannot see, cannot weigh, and cannot explain. There's a strange comfort and a strange terror sitting together in this. The comfort is that we did it. We took the most elusive part of the ordinary matter, the gas that hid for decades, and we found it, weighed it, started to map it. The method works. The dark can be made to give up its secrets, at least sometimes, at least in part. That's a genuine reason for hope about the larger darkness still ahead. The terror is the scale of what's left. If the easy 5% took this much, flashes from dying stars, arrays of dishes, decades of work, to pin down, then the 95% we don't understand is a problem of a different order. The web cradles the galaxies, but the web itself hangs on the dark matter we can't see, inside a space being stretched by the dark energy we can't explain. Most of reality is still out of reach, and yet the missing matter shows the way the reaching is done. Not by waiting for the dark to shine, which it never will, by finding some signal that crosses it and comes back changed, some flash that the darkness writes itself into, that we can learn to read. That's how the ordinary matter fell. It may be how the rest falls too, one clever signal at a time, which brings the whole story back to where it started, and to you. Because the matter that was missing, the gas in the web, the stuff we finally found, is not separate from you. It's what you're made of. And knowing where it's been changes what you are. Add up every star you can see, and you've counted less than 1/10 of the ordinary matter in the universe. We started there. Now you know where the rest of it is. It's between the galaxies, in the thin, warm gas of the cosmic web, in the threads and the dark. 3/4 of all the ordinary matter there is, spread across distances that crush the mind. It hid from us for the whole of human history. It took flashes from dying stars billions of light years away to find it. And it was there all along. The bulk of the touchable universe, in the part we'd called empty. That was the question we set out to answer. Where did the missing half go? It went into the dark, blown there by the violence of black holes and dying stars, and held in a web so faint we stared straight through it. The answer is settled now. The missing matter is found. But the answer turned the question around on us. Because that gas, the missing matter, the stuff in the web, is the same stock your body is drawn from. The iron in your blood, the oxygen in your lungs, the calcium in your bones, was forged in stars, blasted out into that thin, warm haze, and drifted in the dark between galaxies for ages before gravity drew it back in, and a small part of it became you. You are made of the missing matter. You always were. So the gas in the web is not a distant abstraction. It's where your atoms have spent most of their existence, and where they'll return when you're done with them. You are a brief gathering of the cosmic web, a place where the missing matter paused for a lifetime, and became something that could look up and ask where it had been. The dark between the galaxies is not foreign to you. It's home, the place most of your material has lived. the place it's only visiting your body on its way back to. Most of what you are has spent most of time in the dark, in the cold, thin gas between the galaxies, in the part of the universe that gives off no light. You are the rare moment when some of it gathered and warmed and woke up. You are the missing matter, found